This is an AQA A-level chemistry year 13 topic. This is part 5 of the acids, bases and buffers topic, and in this video we're going to focus on indicators and half equivalence. Going to recommend you pause, have a go, see how you do, see what's going well and what might need a little bit more attention. So when we are looking at indicators, we need to be able to describe how pH curves can be used to decide what indicator we will use. And you are going to have to learn some specific facts about a couple of these, specifically methyl orange and phenolphthalein. Now, an indicator changes colour when it moves from the acidic to the alkali environment, but different indicators will make that change at different points. You can see, for example, methyl orange, it will change, the colour will change in the range of around 3 to 4.7. Bromothiamyl blue will go from 6 to about 7.5, and phenolphthaleine's change will be about 8.5 to 10. For an indicator to work, that colour change has to happen where there is a rapid change in pH on the addition of small volumes, and it's really quite useful to watch this video in conjunction with part 4 where we look at pH curves, but we are going to revisit those in this video as well. So we would get the rapid change in the area that I've highlighted. Now if I put up a strong acid strong base, strong acid weak base, weak acid strong base and weak acid weak base curve, we can now start to work out where we would be able to use which of the indicators that we've got listed. And I'm going to highlight them so I can put some information directly on. I've color coded them appropriately, so methyl orange is orange, bromothiamyl blue, blue, phenolphthalein is that characteristic pink color. Let's begin with methyl orange, and I'm going to very roughly, not doing this accurately at all, but I'm going to sketch on to the 4 curves where we would get the colour change for methyl orange. And you can see that there is a rapid change in a strong acid strong base and in a strong acid weak base, but actually the change might happen below the pH of the acid in the case of the weak acids. So weak acid strong base and weak acid weak base, methyl orange would not be a suitable indicator, but it would work in a strong acid strong base and a strong acid weak base. Let's move on and take a look at bromothiamyl blue, which changes around 6 to 7.5. Well, it would work with a strong acid strong base. It would sort of work with a strong acid weak base, though you're getting a little bit of a lip there depending on where you would actually be seeing the change. We would definitely get the change on the weak acid strong base in the right place, but it would not work with the weak acid weak base. And finally, we're taking a look at phenolphthalein. It would work with a strong acid strong base, definitely not with a strong acid weak base. It would sort of work with a weak acid strong base there that we can see, but not with a weak acid weak base. So your role when you're choosing an indicator would be to think about either I'm provided with data where the rapid change occurs, does that tally with a rapid change in pH on the pH curve? And if it does, then it's suitable. But also it's important that you remember that methyl orange changes at a low pH, and that makes it suitable for anything with a strong acid. Phenolphthalein changes at a high pH, which makes it suitable for anything with a strong base. They are the 2 that I would recommend that you learn and recall so that you can answer those questions quickly and effectively. Okay, we're going to finish off this video though by looking at half neutralization point, which is a very specific question about a very specific quirk of something that we take from pH curves. So I am going to say, have a look at these questions, work through them. I've tried to make it as logical as possible to build to the final answer, and you can see how far you get. So in the first instance, I'm looking at the graph, and where the equivalence point is, where we get that rapid change is 25 cm cubed. If I were to write an equation to show what happens if I add OH minus my ions to HA, well, I'm neutralizing them. So my HA plus OH minus goes to A minus plus H2O. Next question. Half equivalence is the point at which half of the volume needed to reach equivalence has been reached. What volume is needed for this? Well, that's simply halving that value of equivalence point. So it's 12.5 cm cubed. And what can be deduced about the relative concentrations here of HA and A minus? Well, what's important here is if you think that you've got 100% HA at the beginning and 0% A minus, when I fully neutralize equivalence point, it means I've got 0% HA and 100% A minus. So halfway, I would expect half of my HA to have been converted and half of my A minus to be formed. So it actually means that they are equal. Concentration of HA equals A minus. So I'm going to put the expression in as the question asks for, H plus times A minus over HA. But let's actually see how we can simplify it. I'm going to put it down here as well. We're saying that at half equivalence, A minus is equal to HA. Well, that means we can cancel them out. And that means that at half equivalence, very specifically, Ka is equal to H plus. Now, we also know that pKa is negative log to the base 10 of Ka, and pH is negative log to the base 10 of the concentration of H+. It's the same expression with different values. So that also means that if Ka is equal to concentration of H+, pH is equal to pKa. Now that can be really useful for using the graph to find out pH values. That takes us to the end of this video. Thank you for listening and goodbye.